Exceptions to VSEPR and hybridization. This section actually comes a bit early in your textbook, but I saved the discussion till the end because I wanted to discuss the correct way and the most common shapes of molecules. And I wanted to save the exceptions for the end. So these are exceptions to the octet rule. When it's necessary to exceed the octet rule for one of several third row or higher elements, place the extra electrons on the central atom. That's what you saw me do in our expanded octet. Whenever there were extra pairs of electrons that needed to be taken into consideration, I always place them on the central atom. So for example, SF4 and ASBR5, which have, you can see, respectively 34 and 40 electrons. Notice that with SF4, there's going to be a lone pair of electrons, and that lone pair of electrons you can see right here off of sulfur. ASBR5 is just an expanded octet. It would be a trigonal bipyramidal. This is an exception to the octet rule, or expanded octet. So let's draw the Lewis structure for each of the following molecules. BF3. So how would we do that? Well, let's see. BF3 is a pretty straightforward one. Boron, you'll notice, if we go to the periodic table, only has a valence of 3. And therefore, if it has 3, and fluorine has 7 times 3, which is 21, so that's 24 dots or 12 dashes, we're going to have this 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one is going to be trigonoplanar because those electrons are going to get as far apart as possible. There's 3 fluorines. Now, it appears that boron is incomplete, and we haven't followed the octet rule. But essentially it is, because what happens is boron loses its 3 valence electrons, one each to each fluorine, and the lower levels of boron are actually filled. These pictures, these Lewis diagrams, cannot show that because they only show the valence electrons. So that's why they call it an exception. We didn't really call it an exception. What we had said was, because boron is acting like a metal and it's going to lose its electrons, it will look incomplete in these pictures. PCl5. Now this one is one that's going to be an exception, or an expanded octet. Phosphorus, going to the periodic table, has 5 valence electrons. Chlorine has 7 times 5, or 35. That gives us 40 dots, or 20 dashes. So PCl5, you can already see, is going to be an expanded octet, probably a trigonal bipyramidal. PCl5, so that's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And that's exactly right. It's one of those expanded octets. And SF6. I think we've already done this one, but this will be an octahedral. I'll leave you that one to do if you want to practice. So let's review. Carbon, nitrogen, oxygen, and fluorine should always be assumed to obey the octet rule. Notice those are the smaller ones of that particular families. Boron and beryllium have fewer than 8 electrons around them in their compounds. Second row elements never exceed the octet rule. Again, the smaller the atom, the less likely that can happen because they can't accommodate additional things around them because the nucleus and the valence shell is so close. Third row and heavier elements often satisfy the octet rule, but can exceed the octet rule by using their empty valence d orbitals. As I said in a previous discussion, the paired electron can be separated and be promoted to the d sublevel. When writing the Lewis structure for a molecule, satisfy the octet rule for the atoms first. The electrons remain after the octet rule has been satisfied, then place them on the elements having available d orbitals, those in period 3 or higher. So we've already talked about that as the expanded octet. Here's a new topic for us. It's resonance. Sometimes there's more than one valid Lewis structure that can be drawn for a particular molecule. For example, NO3. Now, if you add up the total number of electrons for NO3, you're going to have 24, which would be 12 dashes. So it sounds like it's going to be pretty easy. And if I draw it over here, and it's NO3 negative, by the way. That's how we got 24. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, I can't do that. I have to remove one of those and make it a double bond. Now, I happen to choose this one as a double bond, but who says it couldn't have been right there? Or right here? In fact, if I wanted to, I could have moved a different pair of electrons, and the double bond could have been between the top oxygen and the nitrogen, or the right-hand oxygen and the nitrogen, and in fact it wouldn't really matter. It was just my choice to place that one where I did because it was the last one I happened to draw and it was easy to remove. But it would be unstable for the molecule to look like this, to have a double bond here and some single bonds here. Remember, double bonds are shorter and stronger than single bonds, and so it would make the molecule uneven. And who said that that oxygen is any more important than those other two? Why is that one getting the double bond? So in fact, this is what happens. I know it looks a little crazy. Notice the square bracket as well, which I didn't put because it's an ion. But notice what's happening, the way it was drawn. The first picture shows the double bond right here. The next one shows the double bond here, and the last one shows the double bond here. In other words, any of these pictures are good enough. And you notice they put them in the square brackets because it's an ion, and then they put this double arrow between, meaning it kind of goes between all of these. In fact, what happens is the electrons don't just hover around one nitrogen and oxygen. They kind of move between the entire structure, or they resonate. So they vibrate between the different ones, so that in fact, instead of having a double bond and two single bonds, it's like they have a 1 1/3 bond between all of those structures. Everybody gets a little extra. Let's see what the slideshow is telling us. The actual structure is an average of the resonance structures. Electrons are really delocalized. They can move around the entire molecule. That's exactly what resonance is. So let's draw a Lewis structure for each of the following molecules. Some of these may have Lewis structures, resonance structures, and some may not. Let's see if any do. All right, I'm going to start with CO2, and I'm actually going to leave CO because I think that one's the hard one. So CO2, I think we've done before in intro. This one will look like this. And I'm angling my lone pairs to make it look even. There's some double bonds between carbon and oxygen, and that satisfies that one. I'm going to draw CH3OH next. This one's pretty straightforward. This one has two centers. So there's the CH3OH. This one actually has some double bonds. And I'm not going through how to figure out the number of valence electrons and dashes and dots. I'm going to leave that up to you. Notice in this picture, if we had to say the shape, this one would be tetrahedral, and this one would be bent. This one, of course, is linear. That's the shape of that molecule. All right, OCN negative. Now, I have to remember, because it is an ion, I'm going to put it in a square bracket. I've been forgetting to do that in the last couple slides. So I'm going to do it right this time. So we have carbon in the middle. When in doubt, carbon goes in the middle. And then I have OCN. When I work it out, I'm going to have a triple bond with nitrogen, and that, and -1. And that 2 is linear. And then CO. CO is an interesting one. Usually carbon does not have a lone pair, but That's the only way it's going to work out in this case, because of formal charge, which we'll talk about later. So carbon, oxygen, CO, carbon monoxide. Again, a little unusual, but that's how it works. So let's talk about formal charge. I mentioned it a minute ago. It's used to evaluate non-equivalent Lewis structures. Atoms and molecules try to achieve formal charges as close to zero as possible. Any negative formal charges are expected to reside on the most electronegative atoms. How do we get formal charge? Well, it's the number of valence electrons on the atom minus the number of valence electrons assigned to the atom in the molecule, assuming that the lone pair electrons belong entirely to the atom in question, and the shared electrons are divided equally between the two shared atoms. So, how do we calculate this? To calculate the formal charge, take the sum of the lone pair electrons and 1/2 of the shared electrons, and from that you're going to subtract the number of assigned electrons from the number of valence electrons on the atom, on the neutral atom. So, this is how I might think about it. I'm going to take formal charge is going to be like the number of valence electrons minus the number of lone pair electrons plus 1/2 of the electrons that are in the bonding pair, because it doesn't just belong to one atom, they have to share them 1/2 and 1/2. Alright, so let's check it out. Here is the Lewis structure for POCl3. Assign the formal charge for each atom in the molecule. Now, don't think of charge as an ion. You know, like oxygen's -2, chlorine's -1, phosphorus -3 usually. So the question is a little bit different here. So how are we going to do it? Well, let's check it out. Phosphorus. Remember the little decoder I gave you last time? Phosphorus has 5 valence electrons. You can check that out on the periodic table. That's where this 5 is coming from. Then you notice there are 4 bonds here. Each have 2, or 8 total. But they have to share them between the other things, chlorine and oxygen. So that's where we're getting this 4 from. 8 minus 4 is 4. So it has a charge of +1. Remember, they try to be as close to 0 as possible. +1, -1 are okay. Let's look at oxygen. Oxygen has a charge of, or has a valence of 6. Now, you'll notice here, it has 1, 2, 3, 4, 5, 6 lone pairs, and 1 bonding pair, which is a double, but we're going to only count it half. So 1, 2, 3, 4, 5, 6, 7, and that's where we're getting 6 minus 7 or -1. And then finally chlorine. Chlorine has a valence of 7, and it also has 7, 1, 2, 3, 4, 5, 6, 7, or a formal charge of 0. So that's what formal charge is. The sum of the formal charges of all atoms in a given molecule or ion must equal the overall charge on that species. If non-equivalent Lewis structures exist for a species, those with formal charges closest to 0 and with any negative formal charge on the most electronegative atoms are considered to best describe the bonding in the molecule or ion. And that's the reason carbon monoxide has carbon with a lone pair, because the other choices one could have would allow for higher formal charges. So we want to be as close to 0 as possible. Here's another example. They're showing this. This is carbon dioxide, which is what we drew correctly. This is the correct one. If we check out the formal charge, it's most even and lowest for this one, and that's why that's the correct structure. Oh, there they go.